unit step function. Unit step function, it is denoted by u of t, that is defined as 1 for t greater than 0 and 0 for t less than 0. This is the definition. I think I have mentioned it in the previous last tutorial class. This is how we define a unit step function. For there is a discontinuity at t equals to 0. Forget about that discontinuity. What is interesting to us is what is happening after the discontinuity and before the discontinuity. So if we sketch this, it's like this, 1, 0. This is the plot of that unit step function. And I have already explained that we can model, for example, if we consider this, let's say there is a voltage source, 1 volt, 1 ohm resistor, and if the switch is closed if it is open and it is closed at 0, then we can represent the voltage across this resistor with this waveform, isn't it? Unit step function. Okay, again, like the sinusoidal signals and complex exponential signal, this is also a hypothetical signal. Hypothetical signal means we cannot, is it possible to realize this physical realization of this signal? Is it possible?
No, sir.
No. What is the problem?
Sir, it will take time to go from 0 to 1. It cannot instantly.
It is not, that is one thing, and even if it can go instantaneously from 0 to 1, what will happen? What about this? What is the energy of that signal? What is the energy of a unit?
Infinite.
It is infinite. So if we want to generate such a signal, the source must have infinite energy. So that is not practically possible, isn't it? Okay, so that's why we call it hypothetical signals, but these are extremely useful in the analysis of signals and systems. Okay, so for example, if you are closing this switch at t equals to 0 and again opening after, let's say, so it is closed for 5 seconds only from 0 to 5. Now what is the waveform? What is the voltage output voltage across the resistor? Is it this 0, 5, 1? Is it the voltage waveform? Closing the switch at 0, opening at 5. So 0, this is the waveform, isn't it?
Yes,
Now,
sir.
can we express this in terms of unit step function?
Yes, sir.
What is that expression?
U0 minus U5.
What U0 minus U5? What is U0?
U0. Sir,
Is it UT minus 5?
yes, sir.
U0 is the value of the function at 0, isn't it? And U5 is the value of the function at 5. Okay, so these are the functions. That means you take this function, this is ut 0, and if you are subtracting a shifted version of that, this is ut minus 5. If you subtract this, you will get this, isn't it? Again, forget about the discontinuities. Don't ask me what is the value at this point, means at t equal to 0 and 5. Forget about those discontinuities for the time being. We'll discuss about that later on. Okay. And the discrete time counterpart of this unit step function is it is called unit step sequence. Okay. It is also called unit sample sequence. It is defined as, the notation is same, un, because it is a discrete time signal. It is defined as 1 for n greater than or equal to 0 and 0 for n less than 0. Okay, so this is the discrete time unit step sequence because it is a discrete, the independent variable is a discrete variable. So here you can see that there is anyway it is a discrete sequence, so there is no discontinuities because the value that function is defined only for integer values. isn't it? So it is the shape of the, if you sketch that, this is that function. Now if we have a function like this, 1, 2, 3, and it is 0 for all the values of n. So can we express this in terms of unit step sequence? What is the expression in terms of un? Suppose we have a signal like this. It is 1 for okay, let's say 1, 2, 3, or let's say 0 to 3 it is 1, and for all other values it is 0. What is the expression for this signal in terms of unit sample sequence?
un minus 4.
It is un minus 4, isn't it? It is un minus 4. So you have to be careful about this value un minus. It is not un minus 3. In the case of continuous time signal, if we consider continuous time signal 0 to 3, then it is ut minus 3, isn't it? But for discrete time, it is un minus 4. Okay. Now let us discuss another signal, basic signal, that is extremely important in our study of these signals and systems. That is called the impulse function. First, let me give you an example. Consider a voltage source, and instead of resistor, let's consider a capacitor. Let's say the switch is open for a long time, and then the capacitor is initially discharged, and it is closed at time 0. Okay, and this is 1 volt, and let's say this is 1 farad. What is the voltage across the capacitor? What is the voltage across the capacitor? What is the what will be that waveform of Vt? For t less than 0, what is the value of this voltage? We are assuming that it is initially discharged and the switch is open, so it is 0. Now, what is the voltage across the capacitor after t greater than 0? For t greater than, it is 1, because KVL must be satisfied, isn't it? At any instant of time, KVL must be satisfied. So at the moment we close this switch, this should reach 1 volt voltage across the capacitor. Okay, then only KVL will be satisfied. Okay, so now what about the current flowing through this capacitor? Someone told that it is 0 volt. Is it 0 volt?
Infinite for just a moment.
Infinite for just a moment. What is the reason for that? Otherwise, the capacitor should charge instantaneously from 0 to 1 volt at 0, isn't it? When t is equal to 0, the capacitor should charge instantaneously from 0 to 1 volt. And what is the capacitor charging that equation? Is it integral minus infinity to Vt, that is equal to integral minus infinity to t? Okay, forget about this because we are assuming that it is a 1 farad capacitor. So this is the capacitor charging equation. Now, in order to change this voltage instantaneously from 0 to 1 at 0, at t is equal to 0, what should be what should be the current flowing through the capacitor? If the current is finite, so basically we have to find this, isn't it?
Yes, sir.
Because for t less than 0, the switch is open, the current is closed. Sorry, the current is 0. Switch is closed, so switch is open and the current is 0. Now at t equals to 0, the switch is closed, so infinite current will flow through that capacitor at that particular instant of time, isn't it? Then only this integral is finite. Otherwise, it is 0. Okay. So modeling this type of signals, we can define a function that is called unit impulse function. Okay, unit impulse function, and that function is defined as, let us consider a signal. Let's say this is a signal. I'm defining it x delta t, and this is and let's say its amplitude is 1 upon delta. Now, what is the area under this this function? What is the area?
1.
It's 1, isn't it? Now, what will happen as we increase? So, if we decrease the value of delta, what will happen? If we decrease the value of delta, what will happen? The width of that function, the support of that function reduces, and its amplitude increases, isn't it? So, if we reduce the value of delta, the amplitude increases and the support of that function reduces. But what will happen to the area? Will it remain the same if we reduce the value of delta?
Yes, sir.
The
Same.
area will remain the same because this is the height is 1 by the amplitude is 1 by delta. Now, what will happen in the limiting case? Limit t tends to limit delta tends to 0. What will happen? What will be the support of that function? Will it tends to 0? As delta tends to 0, the support of that function, that in this case the width of this rectangular pulse, that tends to 0, and its amplitude tends to infinity, isn't it? But the area under that function will remain what?
So the same.
It will remain the same, 1. Okay, so that is the delta function. We can define a delta function as delta t. This is the standard notation we'll be using for delta function. Delta t, that is okay. So this is the definition. Delta t is equal to 0 for t. This is how we define a delta function. Delta t is equal to 0 whenever t not equal to 0, and the area under the delta function is 1. Okay, it is a strange function, isn't it? The function is having non-zero value only at this instant, and we are not defining the value of that function at that particular instant. Is it? This is delta function is a function that is having a value 0 for all the values of t not equal to 0, and the area under the function is 1. It is having only non-zero value at this instant of time, and we are not defining that function. What is the value of that function at that particular instant of time? What is the value? Is it something tending to infinity?
Yes, sir.
So we don't define the value of that function at that particular instant. Instead of defining that value, we define this in terms of this integral. Area under that delta function is 1. Okay, so you can see that this function, this is a limiting case of this. As delta tends to delta tends to 0, x delta t, this is delta t, the delta function. And you can easily verify that it is not necessary that it has to be a rectangular pulse. Any symmetric function having value area 1, let's say this one, this is delta to minus delta. Okay. If you consider this function, the limiting case of this is also delta function, isn't it? As delta tends to 0, this function also tends to a delta function, isn't it? Is it? And this delta function defined like this is called, this is also called Dirac delta function. It is named after British physicist Paul Dirac. Dirac delta function. This is the definition of Dirac delta function. Okay. Now, how is it related to unit step function? Is it related to unit step function? What is integral minus infinity to t? What is this integral? What is the area under an impulse? 1. So what is this function? Is it a function of t?
So u of t.
It is u of t, isn't it? It is not 1. This area is not 1. It is a function of time. Okay, generally we denote this, represent this unit step function, the unit impulse function. This is the representation. This is the plot of delta t. Okay, there is an impulse at 0, and within bracket we mention 1. What is this 1? It is not the amplitude of the delta function. Remember, it is not the amplitude of the delta function. It is the what?
Area.
It is the area under that impulse. So it is the area under that impulse. Generally, we call it as the strength of the impulse. Okay, strength of the impulse. Now, what about this integral? We are integrating from minus infinity to up to this, means up to some time instant t. So is it ut or 1? If you consider some value t here, what is this integral?
0.
It will be 0. So if you sketch this, it will be up to this point it is 0, and then what happens at this point? At t is equal to 0, there is a jump from 0 to 1 because the area under the impulse is 1. And what will happen for t greater than 0?
It will remain.
It will remain this. Okay. So this is the relation between unit step function and delta function. Ut is integral minus infinity to t. So can we write delta t is this true? If unit step function is the integral of delta function, then delta function is the derivative of unit step function. Is it? Is it a differentiable function? Ut? No, it is not a differentiable function because there is a discontinuity, isn't it? So in the true sense, we cannot write this we cannot write delta t as a derivative of this unit step function, but we use this relation in the something called generalized sense. I will explain what is meant by generalized sense. In it is in the generalized sense means we are not interested in the value of this function, the expression for that function, but we are interested in how that function is interacting with other functions. Okay, so I'll give you an example, then it will be clear. Consider a function Okay, before explaining this property, I will have to explain something else. Delta function is defined as it is 0 for t not equal to 0 and integral minus infinity to x delta okay, this is how we define delta function. Now what will happen if we multiply a function with delta function? What will happen if we multiply a function with a delta function? Delta t is 0 for all the values of t, means all the non-zero values of t, isn't it? So can we write this as, is it x0 or x0 into delta t? Can we write like this?
Yes, sir.
It is x0 into delta t, isn't it? Is it? Because this delta function is 0 for all the values of t other than 0. So this is having only non-zero value at 0. So we are writing it as the value of that function at that particular instant of time, x0 into delta t. Is it? Now if we integrate both sides with respect to t, what is on the right hand side?
X0.
It is x0. Then we get that value of that function at that particular instant of time, isn't it? So this is a very important property of delta function. This property is called the shifting property. It is the shifting property of delta function. We can generalize this if we have a function xt. Let's say the function is something like this. And we are multiplying this function with a shifted delta function. Let's say delta t minus t naught. That means it is a shifted delta function. In this case, it is a delayed delta function, delayed by t naught. And here we assume that the value of the function, it is this function x is continuous at t naught, that is x t naught plus this is equal to x t naught minus. If the function is continuous at t naught, if the function x is continuous at t naught, then we can write xt into delta t minus t naught, that is equal to what? What is this? Xt into delta t minus t naught. If we are multiplying,
XT1.
it is xt naught. What is the reason for that? Because the delta function is non-zero only when this is what? When this is 0, t minus the argument is 0. That means t minus t naught is 0. So here it is t minus t naught 0 means t is equal to t naught. Okay. So this is xt naught into delta t minus t naught. Is it that? It is xt naught into delta t minus t naught. Now if we integrate with respect to t, what we get is xt naught. Okay. That is called the shifting property of delta function. Okay, now let us go back to the example that I mentioned. Consider a function phi t. So what did I say there? Okay, we are talking about the relation between unit step function and delta function. I have told that this is delta function. Delta t is derivative of ut in some generalized sense. Okay, I will now explain what is this generalized sense means. So consider a function, some function phi t, and if you multiply it with So what we are doing here is consider a function phi t, multiplying it with the derivative of the unit step function and integrating it. What is this integral? We can do integration by parts. For the time being, let's assume that this is a differentiable function in some generalized sense. Okay. Now, what is this integral? Is it phi t into integral of this, that is ut minus infinity to infinity minus integral? Is it this? Phi dash t
So phi dash t into ut.
into
Right?
ut dt. Is it this?
Yes, sir.
Yes.
Now, can we simplify this? What about the first term? Multiplying a function with ut. What is ut? Ut is this. It is 0 for t less than 0 and 1 for t greater than 0. So what will be this term? First term? Is it this?
Yes, sir.
Because phi of minus, if we apply the lower limit minus infinity, ut is 0, u minus infinity is 0. So this is phi infinity. Now what about the second term?
Phi infinity minus
Sorry.
phi 0.
So can we write it as this integral, because ut is 0 from what? Can we rewrite this integral as integral, let's say 0 plus to infinity
Yes, sir.
because ut is 1 for t greater than 0 and 0 for t less than 0. So we can change the limit and put this as 1. Now what is this integral? Is it this? Phi infinity plus what? Is it this?
Yes, sir.
Okay. So this will get cancelled. So it is phi 0 plus. Is it that? We are considering a function phi t, multiplying it with the derivative of unit step function and finding the integral area under that function. Okay. So here we get phi 0 plus. Now if we assume that the function phi t, if the function phi t is continuous at 0, that means phi 0 plus is equal to phi 0 minus is phi 0. If the function phi is continuous at 0, so can we write this as phi 0? Is it? Is it phi 0?
Yes, sir.
Yes. Okay. Now let us consider this example. I have mentioned that in the generalized sense, this is equivalent to delta t, isn't it? Derivative of unit step function. Now, if we consider that generalized relation, then integral minus infinity to infinity phi t delta t. What is that? dt. Replace this derivative of ut with delta t. Then what is that integral? What is that integral?
Phi
Sir, 5
It is
0.
phi 0, isn't it? Are they same?
Yes, sir.
So generalized sense means with respect to, in this example, with respect to this operation, that means you are multiplying a function with this derivative of ut and finding the area. With respect to that operation, we can replace this with delta t. You will get the same answer. That is meaning of generalized sense. Okay, that function itself is not important. What is important is how that function is interacting with other functions, how it is operating on other functions. Okay, so that is called that is why we say that this is in the generalized sense, derivative of unit step function is the delta function. Okay. Okay, now let us discuss some properties of this delta function. What is delta minus t? Is it delta?
Same as delta.
It is delta t. That means delta t is an even function, is it? It is easy to verify because delta function is a limiting case of this. And if you flip this, you will get the same signal, isn't it? So it is easy to verify. Delta t is an even function. Impulse function is an even function. Okay. Now what about scaling? Assume that a is greater than 0. What about this? Is it delta t? We are considering delta function as the limiting case of this. Let's say this is x delta t and this is delta by 2 and minus delta by 2. Okay. Now can we say that this delta at, this is a limiting case of x delta at? Is it that? If you scale means both sides you scale by a factor of a. Is it? Now tell me what is this? The limiting case of this. What will be the area? When you consider this function x delta at, what will be the shape of this function x delta at? It is time scaling operation. What is the shape of that function? Is it a rectangular pulse? Time scaling operation preserves the shape of the function, isn't it? Now what about this point? Which point is this? Which point is this?
Delta by 2.
Delta by what? Delta by 2a? Is it that? Or a into delta by
Yes,
2?
sir.
It is delta by 2a. And this is minus delta by 2a. And what about the amplitude? Will it change the amplitude? It is delta at means it is time compression. We are squeezing that signal in the time domain. The amplitude will remain the same. So what is the area under this? What is the area?
1 by a.
It is
1
1
by
by
a.
a. So what will happen in the limiting case? As delta tends to 0, the support tends to 0 and the amplitude tends to infinity. So can we say that delta at is this true?
Yes, sir.
This is the relation. Now here I assume that a is greater than 0. So we can, this is mod a. Okay. Okay. Now if we consider, let's say, a step function, a rectangular pulse, 0 and let's say 2. This is the signal xt. What is the derivative of this? Let's say the height is 2. What is the derivative of this function?
Four.
Sorry, 4? What?
4 units.
4?
Right.
4 units. Okay, first of all, what is the derivative of this if we consider a step function with height 2? What is the derivative of this? It is 2 times delta t. Then only if you integrate it, you will get 2 ut, isn't it? This is 2 ut. This is 2 times delta function. So can we say that if there is a jump discontinuity, and if you find the derivative of that function, at the discontinuity, you will get a delta function. And what will be the strength of that delta function? Strength of that, this is called the strength of the delta function. that strength of the delta function is it the height of that jump discontinuity?
Yes, sir.
It is the height of that discontinuity. Now tell me what is the derivative of this function? So at this point it is 2 delta t, then
Delta function minus 2 times
minus
delta t minus 2.
delta t minus 2, isn't it? It is 2 delta t minus, there is a shifted, there is another impulse here. The strength of that impulse is minus 2. That means area under that impulse is minus 2. Okay. So this is the derivative of that function. So this you have to remember whenever there is a jump discontinuity, and if you find the derivative of that function at the discontinuity, there will be an impulse, and the strength of the impulse is equal to the height of that jump discontinuity. Okay. Now let us consider another function. Let's say xt is e to the power minus t minus 1 ut minus 1. What is the shape of this function? Xt is e to the power minus t minus 1 ut minus 1. Is it a shifted version of e to the power minus t ut?
Yes, sir.
You replace t with t minus 1, that is delay by 1, you will get this function. So is it a function like this? Exponentially decaying, this is 1, it is 0 up to this point. Is this a function xt? Is it?
Yes, sir.
Yes,
Now
sir.
what is the derivative of this function? What is the derivative?
Dirac delta function of t minus 1 into e to the power minus t minus 1 plus minus of e raised to power minus t minus 1 into u t
Yeah,
minus
because
1.
this is a function of t and this is another function of t. So you have to apply the chain rule. So this is minus e to the power minus t minus 1, the derivative of this, into ut minus 1 plus what? E to the power minus t minus 1 into derivative of ut minus 1. What is the derivative of ut minus 1? What is the derivative of ut minus 1? That means it is a,
Dirac delta function.
yeah, it is a shifted unit step function. So there will be an impulse here, and the height of that impulse is what here? It is 1, isn't it? So it is delta t minus 1. Now can we simplify this part?
So 1.
Is it 1?
0 for t not equal to 0.
No, we have discussed that property. If you take any function xt, and if you multiply with delta t minus t naught, what will be the function? Resulting function? Because
X of t naught.
T naught.
it is not x of t naught into delta t minus t naught, isn't it? X of t naught is a constant. It is x of t naught into delta t minus t naught, because the delta function is non-zero only at this point, isn't it? And other values it is 0. So at this point it is x t naught into delta t naught. Okay, so this is the resulting function. Now tell me what is the simplified version of this? This part, second part.
Delta of t minus 1.
It is delta, so we can, it is e to the power minus t minus 1 ut minus 1 plus delta t minus 1, isn't it? Because this function is non-zero only when t is equal to 1. So when t is 1, this term is 1. So it is delta t minus 1. Okay. So another important function is the unit ramp function. Unit ramp function is defined as, it is denoted by RT, it is TUT. So TUT means this is the unit ramp function. Okay, unit ramp function. Now, how is it related with the unit step function? How is it related with the unit step function? What is the derivative of this? What is the derivative of this ramp function?
1 for t greater than 0, 0 elsewhere.
So is it unit step function?
Yes.
So, or we can say that RT is the integral of the unit step function, isn't it? Ramp function is the integral of the unit step functions. And all these functions, we have seen that all these functions are related: delta function, unit step function, ramp function. All these functions, they belong to a special class of functions known as singularity functions. Okay, singularity functions are the functions that are either discontinuous or having discontinuous derivatives. For example, in the case of ramp function, is it a singularity function? Is there any discontinuity?
Yes.
There is no discontinuity here, but its derivative is discontinuous, isn't it? Derivative is unit step function that has a discontinuity. And unit step function, anyway, it is having discontinuity. So singularity functions are the functions those who are having those who are either discontinuous or having discontinuous derivatives. Okay, so these are all the singularity functions. Now let us consider the discrete time counterparts of these signals. I think we have already discussed UN, that is a unit step sequence. It is defined as 1 for n greater than or equal to 0 and 0 for n less than 0. This is called the unit step sequence. It is also called the unit sample sequence. It is a discrete time signal. Now similarly, we can define the discrete time impulse function. This is called the Kronecker delta function. Okay, in the case of continuous time, it is called the Dirac delta function. Dirac delta function. And discrete time, this impulse function, this is called Kronecker delta function, and this is defined as and this is also called, in the case of discrete time signal, this is also called unit sample function. Okay, impulse, or because impulse does not make any sense in in discrete time, because there is there is no discontinuity. Like in the case of continuous time signal, impulse signal, the amplitude of that signal tends to infinity at t as t tends to 0, isn't it? But here it is a discrete time signal, so there is no such discontinuity here. So this is generally called a unit sample function or Kronecker delta function. Now, how is it related with the unit step sequence? Un and delta n, what is the relation? This is delta n 0 and it is 0. This is delta n, and what is un? Un is 1 for all the values of n greater than 0. So 0, 1, 2, 3, 4. Okay, this is un. Now tell me, what is the relation between un and delta n? Sorry, please be louder. Hello?
U of n minus U of n minus 1.
You are you saying delta n is un minus 1. That is the first difference, isn't it? Un minus 1. It is similar to that of the continuous time case, where there it is a first derivative. Here it is the first difference, un minus 1. Okay. Now how to write un in terms of delta n?
So sigma delta n minus k
Sigma
for k.
delta.
So delta of n minus k for k is equal to 0 to infinity.
Or is it this? Is it this? Is this the relation? What is the meaning of this? This is a delta function. You are summing from minus infinity up to a point n. That is un. So if n is less than or equal to minus 1, what will be that sum? 0. And for greater than or equal to 0, it is? Sorry? It is 1. So is it the unit step function? Unit step sequence? This is the unit step sequence. So this is the expression. And it is similar to the integral in the case of continuous time signal, isn't it? So in the continuous time case, ut is integral minus infinity to t. The only difference is that here it is the integration, and here it is the summation. Okay. Now similarly, we can define this unit ramp sequence. Unit ramp sequence is okay.